Hello and welcome to our today's webinar about the optimization of a centrifugal pump with the aid of computational fluid dynamics. Yes, my name is Milad, and it's a big pleasure for me to welcome so many attendees who are interested to learn more about our today's topic. Let me just introduce myself quickly. My name is Milad, and I'm working for more than 10 years in the field of computer-aided engineering. And for 4 years now, I'm working at SimScale as a product marketing manager. And as a part of my role, I'm preparing and conducting webinars and workshops about different topics to introduce new users to the world of simulation. Yes, let's now take a look at our today's agenda. We will start with a crisp part where I will introduce you to the fundamentals of computational fluid dynamics, and also where we'll also talk a little bit about our cloud-based CFD platform SimScale. After that, we will start to discuss how you can use CFD for pump design and which kind of design scenarios can be leveraged by using computational fluid dynamics. For this purpose, we've prepared what we call a live demonstration. So a real-world industrial CAD model, which we've used to prepare a simulation. And we will discuss the results of the simulation and try to understand how we can use CFD to optimize the performance and the energy efficiency of a centrifugal pump. Yes, and after that we have a dedicated time slot for a Q&A. So in the case you have questions, just write them using the question toolbox, which is integrated in GoToWebinar, the tool we are using to deliver you with this live webinar. And I will try to answer the questions on the fly or latest during the Q&A. All right, let's start with our introduction to SimScale and simulation. And just before we start to discuss the several benefits of simulation, just let's make sure that everybody knows what we are talking about and we all have the same idea about what simulation actually is. And well, engineering simulation actually, or also called CAE, is a word which is used to describe different techniques and different approaches to numerically calculate field values, which can be, for example, pressure and velocity of a fluid flow, but you can also use these techniques, for example, to calculate stress distributions into structural parts. And all of these methods which we are using at SimScale, they have one thing in common, that they actually, you don't calculate a 100% accurate solution, but you approximate the field values. And in the end of the day, this allows us to virtually perform experiments. So, and in the case of fluid flow simulation, we can use computational fluid dynamics and virtually perform this test. So we don't need to have a wind tunnel or another physical test rig. We don't need to manufacture a prototype. Everything can be done virtually. And that means that we have a lot of advantages. And first of all, and this is maybe the overall summary of the benefits of simulation. With the help of simulation or CFD, we can test design correctness and efficiency, and this without building a physical prototype. And in the long term, this can help every engineer in the world to massively save time, to minimize the risk of failure, and also to reduce costs. And this does not necessarily mean that you replace all your physical testing with simulation, but a lot of our customers and users use physical testing together with simulation. And usually what you do, you try to, especially at the very early stage of the product design, you try to test around with different design scenarios, different alternatives, and as later in your design process, when your design is more mature, usually you just use some physical experiments to validate your simulations. Yes, and simulation, especially CFD, so fluid flow simulation, is used in a lot of industries. And from what I've told you, you must think, well, this is so great, it must be industry standard. But the truth is, it's not. Actually, only 1 out of 25 engineers has access to engineering simulation. And there are a lot of reasons why simulation is not adopted widely. And in the end of the day, you can say you can reduce this to three big problems CFD comes with. First of all, you need, when you go work with traditional on-premise software, you have a really big initial investment. So you need to buy the software, which can cost you around 30 to 40,000 euro a year. You need to buy dedicated hardware. And especially for small companies or for single engineers, it's really hard to find a case where such a big investment makes sense, because usually you don't have the time to really use this infrastructure and use the CFD tools 24/7 hours a day. And despite from this, another big problem is that you usually need a very special infrastructure to run the simulations. Because in the end of the day, what the computer is doing, it's solving a really big equation system. And as I mentioned, you usually need very powerful computing hardware for this. And usually you use what you call a computing cluster. And maintaining and updating this infrastructure is not very simple. And this is also a big problem, especially for small companies, that it's not only about having the tools and the hardware, but also the right people who can just maintain the infrastructure the engineers need in the end. And finally, most of the simulation tools in the past were designed for simulation experts, but not for engineers, or let's say for those people who are going to design the products in the end of the day. And that were the reasons why more than 4 years ago SimScale was founded as a spin-off of the University of Munich. And SimScale is the world's first web and cloud-based simulation platform, which gives you the unlimited performance of computer-aided engineering at your fingertips through a standard web browser. And the great thing is the only thing you really need to access SimScale is a standard web browser and a working internet connection. And everything else, so like the computational resources, the software, etc., will be provided through the cloud. And SimScale is actually the first world web and cloud-based simulation platform. And this is really a big change. And I would like quickly to introduce you just to some of the most important and unique features of SimScale. So first of all, SimScale is what we call an all-in-one tool. Traditionally, if you want to start with CAE, you need to buy for every field of physics a different tool. For example, let's say you want to improve your pumps. And then you need to buy a single license for the fluid dynamics model. You need to buy a single license to do the structural simulations and so on. And with SimScale, it's all in one. So all the users have access to exactly the same features, and there is no hassle with different licenses. The next very important point, and that's from my point of view the most important thing, SimScale is super fast and easy. Since it's cloud-based, you're not limited anymore by any hardware restrictions, and you can actually work on your simulation from everywhere, and you will get your simulation results super fast, since you can use up to 96 cores in the cloud. And this is not the only advantage which results out of the cloud-based approach. SimScale also comes with a real-time support, which means you can reach out to our user success team by chat, phone, and by email. And beside support, we also offer consultancy and free learning resources like webinars and trainings. And maybe that's the most important point for most of you. SimScale is super cost efficient, and actually, SimScale is even for free, so you can start with our free community account, which will give you access to all features. And if you say, well, I want to use it, let's say, really for commercial projects, and you need some more confidentiality, you can also start and switch to our professional plans. And the final 2 points, security and collaboration. So based on our cloud approach and the cloud technology, SimScale is not only a web-based tool, but really a community. So we have more than 100,000 users. We have thousands of public accessible projects you can import. And nevertheless, SimScale is still a very secure environment for developing products, since we are encrypting your data several times at different stages. Yes, and finally, before we start to take a look at our today's example, let's just try to understand where simulation is used currently. So one very big sector SimScale is used so far is the AEC sector, so architecture, engineering, and construction. And there, SimScale CFD capability is used, for example, to calculate wind loads on facades of tall buildings or to optimize the thermal comfort inside large rooms. But besides, the SimScale is also heavily leveraged by other industries and completely different applications. For example, we have customers from the field of healthcare which are using our simulation tools to optimize the performance of medical devices and to make sure that they will work as accepted. But another very big industry where SimScale is used for sure is the valve and pump industry, where it's crucial to reduce the risk of cavitation, for example, to maximize efficiency and reduce pressure drops. All right, I hope that this kind of introduction helped you, and now let's start to talk about our today's topic. And as you know, we will talk today about how CFD can be leveraged to optimize the design of a centrifugal pump. And centrifugal pumps are very important in the industry. And let's say in the last years, due to the increased demand for energy efficiency, also this industry is under pressure. And one of the biggest fields of optimization for a pump, obviously, is the fluid dynamics or the hydrodynamics inside the pump. And that's what we want to do today. We want to do a flow simulation of our centrifugal pump, try to, first of all, to be able to predict performance and energy efficiency, but also to see if there are any, let's say, potentials for optimization. And yeah, that's what we want to do today. So yeah, first of all, this is the case we are going to do. We will, this is the geometry of our pump. You can see the impeller inside. And we will consider a incompressible flow, so with a constant fan inlet temperature of 20 degrees, and the impeller itself will rotate with approximately 160 radians per second, and our flow inlet rate is about 1.1 cubic meter per second mass flow. And let's talk just about some important things and some questions which are raised often. So first of all, a lot of you maybe think, oh, this geometry looks a little different than what I'm using, and you're right. And a very important step of a simulation is actually to prepare your geometry, to make it ready for use. And just think about it. What we are interested in is the flow inside the pump, so the domain which is between the impeller and the housing. And therefore, one of the first things we have to do is to actually extract the fluid region. And this is something we do in our CAD system. You can also do it in theory on SimScale, but usually on your own CAD system it's much more comfortable. And once we have prepared that model, the next step is to mesh it, so to divide it into a finite number of cells. And this step is very important because there we are defining which local accuracy some later simulation will have. And now I would suggest let's switch to the SimScale platform and take a look at the simulation project itself. But before we do that, let's quickly try to summarize what is the aim of our simulation. And by the way, this is a very important point. A lot of people forget to think about what they want to do before they start to simulate. So in our case, we have some constraints, some things we cannot change. First thing is the angular velocity of our impeller, which is, for example, dictated by customers' needs, and the same for the flow rate. And usually, if these two parameters, the angular velocity and the flow rate, are very much related and provided by the needs of your customer. And in the end of the day, what we want to do is to improve the efficiency of our design. And what we can do, therefore, is to change the impeller design or to change the casing design. And the first step we want to do is to prepare the simulation and take a look at the initial state. So therefore, you will now switch to the SimScale platform. Yes, and as you can see, everything I'm doing here now, it's inside my web browser. And I'm logged in with my own account, and I have already copied this project to what we call the dashboard. And from this dashboard, I can access all my simulations. You can see I've simulated the flow around F1 car. We have the centrifugal pump as well. And you can also access our publics project, as I mentioned, by clicking on the public project tab. And here you can see just some of them. And you can see, actually, there is an example for everyone. And for example, if we look for pump, you directly can see a lot of public available pump simulations. However, let's switch back to our dashboard and open the centrifugal pump design project. This project, by the way, was created by my colleague David Lynch, and that's just as an example about the collaboration function of SimScale. I can easily, for example, share the project now with colleagues or with the support, or even make it public available to all of you. But first things first, let's open the project. And in this project, everything is prepared and finished. So let's just go step by step through the different parts and try to understand how we've set it up, the simulation. And SimScale just introduced the new workbench 2.0, and with this workbench, it's even much easier to create a simulation. And the very first step is to import your geometries. And here you have a lot of different options. So you can upload them directly, you can import them from Onshape, and with a direct upload you can actually select a lot of different file formats, including Parasolid, but also AutoCAD, SolidWorks, and so on and so on. Yes, and this is our geometry. And here you can see that actually the model is made out of 3 parts. We have the case, we have called MRF, we'll talk about this later, and we have the actual impeller design. And what we've done, we've actually uploaded 6 different versions. So this is the baseline version, and after you've uploaded your geometry, the next step is to create a so-called mesh. And as I mentioned, the mesh is used, or the mesh is representing the discretization of our domain. So for every center of each cell, we will calculate one mean value for velocity and one mean value for pressure inside the whole cell. Therefore, with the density of the cells, you can control your local accuracy. And why I'm telling you this? Well, maybe a pump is a bad example, but let's say you do a virtual wood tunnel test using CFD. Then you're actually interested in what is happening around the car, so you will use around your object a smaller mesh, and far away you will use a coarser mesh. And here it's the same. If we remove, for example, this face, then we can take a look inside our pump, and you can see how the mesh was refined in the knee of the blades. And you can use a lot of different algorithms for mesh generation. Some of them are fully automatic, some of them need manual parameters. And once your mesh is finished, the final step is to set up the simulation. Therefore, you need to choose the mesh, choose the turbulence model you want to use. As you know, turbulence is still a quite unknown problem. So therefore, since we cannot really resolve these turbulence structures on a small scale, we use turbulence model to reduce the computational effort of our simulation. And then you just specify which kind of fluid is running through your pump, and then you define your boundary conditions. So here we have an inlet boundary condition with a mass flow. Here we have a pressure boundary condition, so we give a gauge pressure, a difference pressure of 0. And yes, for the top of the case, so for the impeller, we've defined a rotating wall boundary condition. Yes, and once this is done, you can actually start your simulation. And in this case, the simulation itself yes, took nearly 800 minutes, but you can accelerate it by using more cores, and then you can take a look at the different results. For example, one thing we have here are the forces on our impeller and the moments, and we can use this later on to calculate the power of our pump. And we can also take a look for sure at the convergence plot. So this is representing how our model is converging through the different iterations. And we can also take a look at the 3D results in real time. And just to make sure you got it right. So right now we are opening like a several gigabyte large file. And usually on a standalone computer in a workstation, this would take a lot of time. But due to our cloud-based approach, it's just a question of seconds until the whole result field is loaded. And then you can take a look at the field values, create slices, and stuff like that. Well, now let's switch back to the presentation. And yeah, just to summarize it quickly. So we actually have 3 steps when we're going to set up a simulation. The first step is to prepare the CAD import. So to upload your model, prepare the mesh. The second step is to set up the simulation itself. So where is the inlet, where is the outlet, define boundary conditions, the material you want to use, etc. And finally, we can take our design decision and take a look and access our results. And there we can access as well the 3D results of the fields, but also like forces, moments, and other stuff. Yes, and as I mentioned, the first thing we did was performing a simulation of the baseline geometry. And now let's take a look at some results. So this is the velocity field inside the base design of our pump. And we can really see how separation of the flow is promoted by the impeller and where recirculation is present. So the colors are representing the flow velocity, where dark blue means a very low flow velocity, and red is a high velocity, around 20 meters per second. And we can really see like that, we have a separation here and even a recirculation. In these blue areas, we are losing a lot of performance. And now let's rotate our slice by 90 degrees. So, and then we can understand how this recirculation is induced. And it's induced by flow separations on the blades themselves. And these separations, they form a separation bubble which gets sucked out of the impeller, as you can see. So, and based on these results, we prepared a sequential optimization of the geometry. So we started with that design and did more and more modifications. And once this was finished, we just ran a simulation of the 5 new designs and compared them. And this is, by the way, a very great thing about the SimScale platform, because since we use Parasolid, you usually don't need to do a lot of modifications with your model, so you can just import a new CAD model, copy your mesh, for example, change the geometry, and 1 or 2 clicks later, your new mesh will be calculated. And well, here you can see now the summary of our optimization study. So the bar chart on the left side is representing the characteristic of the different designs. On the very left is our base design, and in light blue you can see the energy efficiency, and in dark blue you can see the power of our pump. And just to make sure you get it right, so our efficiency is basically dictated by the ratio between energy we put inside the system and what we get out. What we put inside the system can be calculated mainly due to the mass flow, and the power can be calculated based on the pressure forces or the fluid forces acting on the impeller. So this is basically a different direction. Usually you first calculate like your power and then your efficiency, but in the end it will result in the same. And what we can see is that what actually changed is that the power is, yes, let's say on a medium level. So we have like 45 British horsepower. But the efficiency is quite low. And modifying the design will result in a higher overall force on the impeller, which reduces in a higher moment and therefore a higher power. Don't forget, power is a rotating speed multiplied with the moment. And we can see that design change 1 massively increases the power, and design 2 further increase it. And then design 3, 4, and 5, it starts to drop again. And in the end of the day, you can see that we were able to massively increase the efficiency of our design from 64 to 84%. And we also had a version where the efficiency was low, but we have had a very high power. And these are like the, let's say, three design scenarios we can see based on the study. And since our aim was to reduce the energy consumption, we will take we should consider of using design number 5. And the great thing about simulation is it not only provides us with information about for a static point, but actually you can quickly create performance curves for different designs just in some seconds. In our example, we just copied the simulation and tested this for a lot of different mass flows. And here you can see how the design will perform across a range of different flow rates. And this allows us a performance prediction under a range of different conditions. And it's not only interesting for developing the product, but also if you think about the later documentation, this helps you quickly to generate the kind of information maybe your customers need. And if you take a look at that, it's obvious that every design comes with another characteristic, let's say efficiency graph. And the efficiency itself is not only depending on the geometry, but also on the flow performance, on the flow rate. And still, design number 5 seems to be the best. And yes. Now let's take a look at the different other designs. So this is, for example, design number 4. And actually, we improved the recirculation a little bit regarding the flow across the impeller. So it's less here and here, but still, especially in the area of the contact between the housing and the impeller, we still have this 2 big separation bubbles. And if we take a look at the other plane, you can see that the recirculation actually drastically improved in comparison to the base design between the blades, but still, say the areas like around the housing, they still seems not to be perfect. And we can also create very nice animations. So in this case, you can see how the streamlines are traveling through the impeller and through the pump. Yes, and another very important point is cavitation prediction. And yes, as you know, cavitation can be a big problem in pumps, and as cavitation, we describe the effect where due to very high rotating or angular velocities, we can see a formation of gas bubbles. And this cavitation bubbles can really create damage to your pump, and usually to measure cavitation, it's a very hard task because with CFD you can just calculate it based on this formula, and where PV is the vaporization pressure of the fluid, and you have the pressure of the fluid as well as density and the velocity. And for example, now we can visualize areas with a high risk of cavitation, like for example the upper part of the impeller. And in this case, for example, we assume the water to be at 10 degrees Celsius, and therefore the max cavitation number is under 0.7, which is a good identifier for cavitation, and this is something you also need to work on. Yes, and if we take a look at the final results and the return of investment for simulation. So it took us like 3 hours manual time to prepare the simulations, to clean the CAD model, to upload it, to set up everything, and so on. And it took SimScale 6 hours to deliver the simulation results. And for this, we used at least up to 100 cores in parallel per sim. Yes, and the return for us was, first of all, we saved time. You just think about if you want to test something on the physical test rig, how much more time and money it would cost you to prepare the model, to prepare the rig. Overall, we were able to massively improve our design efficiency. It's now 20% higher. And we also were able to show that cavitation is not a big problem for our design, and we gained some insights into this cavitation conditions. Yes, that's from my side. Thank you very much. I hope you enjoyed our today's webinar. We will send you a link with the recording of the webinar in the couple of the next day. And I already answered some questions on the chat. And if there are more questions, please ask them now. And otherwise, you can also reach out to me by email on the mmurphy@simscale.com. Great, it seems like all questions were answered. Thank you very much for staying here with us. I hope you enjoyed it, and see you soon. Bye.